Hello, everyone, and welcome. Thank you for joining us today for our webcast, Apache Cassandra Best Practices and Troubleshooting. We have a great webinar planned for you today. Before we get started, just a few housekeeping items. The presentation will last about 45 minutes. Questions are welcome, and we encourage you to type any questions you have throughout the webinar into the Q&A section on the right-hand side of your screen. We will have a Q&A session at the end of the presentation when all of your questions will be answered. As a reminder, this webcast will be available on demand shortly after the webcast concludes. Please see the attachment section for a PDF version of the slides, as well as some other helpful content. Now, without further ado, I'd like to introduce you to our speaker today, Ben Slater, our Chief Product Officer here at Instaclustr. As Chief Product Officer, Ben has been charged with steering our development roadmap and overseeing the engineering of our products and managing our production support team. Ben has over 20 years experience in systems development, including previous stints with a software product company, and for the last 10 years running large teams for Accenture, a leading global systems integrator. He has extensive experience in managing development teams and implementing quality controlled engineering practices. Ben, I'll hand it over to you.
Thanks, Gina, and welcome everybody, wherever it is, what time of the world it is for you. Thanks very much for joining us for this webinar. So today, basically, what we would like to do is just go through some of the key best practices to consider when using Apache Cassandra. It's a pretty broad survey that we're planning on going through today, so some of the items will be fairly high level, but hopefully still give you some information to at least point you in the right direction and have you thinking about the right things when developing applications and running Cassandra. As Gina mentioned in the introduction, please feel free if anything's unclear to type your questions into the interface, and we'll come back to them at the end of the webinar and make sure that everyone gets their questions answered. So what I'd like to start off with, really just as a bit of a level set, is a very brief introduction to Cassandra and some of the key terminologies, just so that everybody understands those things as I'm talking through them along the way. So as I imagine most people would understand, Cassandra is a distributed database designed to provide extremely high levels of availability and effectively unlimited scalability and scale out by adding nodes, adding servers to your cluster. Cassandra does this by being basically a collection of nodes that are all the same, peers. There's no masters or anything like that, with data replicated across multiple nodes in a cluster, and they all work together as a single logical database. So just some of the constructs that we talk about in Cassandra. A cluster is the highest level of all of the nodes working together as a single logical database. Within that cluster, we have data centers. Data centers, I'm sure, originally were designed to map to physical data centers and often still do in order to provide disaster recovery type capabilities. And each data center operates fairly independently, but Cassandra can keep the data in sync across the multiple data centers. I say they were originally designed to map to physical data centers. Today, they are also often used for logical separation of workloads within a single physical data center. So you can have one online data center and one analytics data center. Cassandra keeps the data in sync between the two, but the workloads are fairly isolated. Within data centers, the cluster is further divided into what are called racks. Racks are used to denote zones where correlation, the chance of failure is correlated. So originally, again, a rack was a physical rack in a data center, which may have shared a power supply or a switch or those kind of things, and that's sort of a single point of failure for multiple nodes. Cassandra takes racks into account when determining how to replicate data so that the data is replicated across as many likely failure points as possible. Then the last couple of bits of terminology that I wanted to talk about were, first of all, replication factor and replication strategy. So the replication strategy and factor are set as part of the schema when you create a table. Well, in fact, a key space, but applies to tables in Cassandra. They determine how many replicas of data Cassandra will store when you write data into a Cassandra cluster. So often, a fairly typical scenario is a replication factor of 3 per data center. That means when you do a write into Cassandra, the node that originally receives the write will replay that write to multiple other nodes in the cluster so that there are multiple replicas of any piece of data. And then if a node becomes unavailable for whatever reason, the other replicas are able to serve reads for that data. The second key bit of terminology I wanted to talk about was consistency level. Consistency level is a property of a query in Cassandra, and consistency level determines how many replicas that are relevant to the query need to return an answer before the query will have considered to have succeeded. So consistency level of quorum or local quorum are fairly commonly used levels, and that means a clear majority of the replicas within the scope have to return before the query succeeds. So for the example of local quorum, the scope of that is within the data center that's connected to, and if you have a replication factor of 3, 2 replicas have to return before the query has succeeded. By using a quorum consistency level and a replication factor of 3, you're able to achieve strong consistency. So all of your reads reflect all of the writes that occurred beforehand, and also to continue to have availability in the face of one replica becoming unavailable or going down. So one replica, if we're using racks, can mean a single node, or it can mean an entire rack, and the cluster will continue to operate as normal because you still have a quorum level of nodes available. So that's a very brief overview, but hopefully for those of you who aren't familiar with Cassandra, at least gives you some idea of some of those terms, because we will be using those later in the presentation. So the first thing I wanted to talk about in terms of best practice, because I think it's the first thing that you will come across, is how to design your data model for Cassandra. So the approach in designing a Cassandra data model is fairly different to designing a data model for a relational database, which many people would be familiar with. The key difference being, with a relational database, your approach is effectively to try and design a model, an entity relationship model that reflects the real world and gives you, reflects all of the complexity of the relationships to the real world. And then you might do some physical optimization after that. But basically, by reflecting the real world, you're confident that you'll be able to store all of the different combinations of data that you might come across, and have a lot of flexibility in how to retrieve that data by using joins and other features of relational databases to get that data out. With Cassandra, you certainly still need to understand the real world and the data, the domain that you're working with, but your data model is driven more by the access patterns that you will be using to retrieve the data, rather than simply reflecting the world as it's modeled. So you need to think about, before you build your data model, how am I going to actually pull that data out? What are the keys that I'm going to need to use to retrieve the data? What's the set of data that I need for any given function? And design your data model to meet that requirement. One of the sort of principles that is behind Cassandra data modeling is that writes and data storage are cheap, whereas reads are relatively expensive. So you denormalize, you write multiple copies of the data, and make it cheap to read the data out by having the data structured in a way that meets the way you're going to use it. So the approach that we recommend in order to sort of put some structure behind how to come up with that data model is outlined on this slide that I have up now. So the first phase would be to understand your data domain. And for me, as someone who's pretty familiar with ER, entity relational modeling, I would sketch out a logical data model in an ER format, possibly even a tool. as a way of understanding what are the entities that I'm working with, what's the data that I need to be able to store. Slightly a different angle that's required when you're doing Cassandra data modeling is that you also probably need to pay a bit more attention to the data demographics, if you like. So which tables have millions and billions of rows in them, which tables have small numbers of rows. So that will be important as you come to denormalizing the data. And then the second thing during the understanding phase is to understand your access patterns. How are you going to select and update data? In particular, what keys are going to be the things that you use to extract the data, but also what's the set of data that you need for any given operation. Once you understand those things, which are kind of your requirements for the data model, you're then basically looking to denormalize your data based on the access patterns. So identify what are the access keys that you're going to use, and they become what we call in this methodology the primary access entities. And then once you've designed those keys, you have to work out how to denormalize the other data that needs to be stored into entities or into tables that are accessed by those keys. And you can do that both by pushing up data, so using collections and those kind of things, and even clustering keys to have a finer grained table, and pushing down data by denormalizing, so having multiple copies of reference data and those kind of things in your table. Both of those things will feel quite weird if you're have a relational data modeling background. And one thing I often say to people is if you have a relational data modeling background and you're doing Cassandra modeling, it should feel weird to you when you start. If it doesn't feel weird, you're probably not doing the right thing and you're trying to put a relational data model into Cassandra. It is quite a different approach. And then the third phase is to review and tune your model. So review the partition keys, check that they have sufficient cardinality, that the number of records in each partition is bounded, and that you've thought about deletes and updates. And we'll actually go through some of those considerations in later slides in more detail. And of course, finally, test and tune. So make sure, and we'll talk later in the deck as well about considerations for testing, Cassandra performance testing and compaction strategies. So that's a very high-level approach to doing data model design, but hopefully gives some structure that you can work through in thinking about your Cassandra data model. Of course, in reality, you won't work through it in such a structured manner, but it does give you a framework to think about. So the next thing I wanted to talk about was partitioning. Partitions are really a very fundamental concept to Cassandra, and the kind of the magic, if you like, behind how Cassandra works and how it's able to scale out. The partition key on a Cassandra table defines, a partition in Cassandra is stored on a single node, or at least a replica of each partition. When data is selected from Cassandra, the first thing that happens is a hash based on the partition keys used to look up which node that data is on. So I have an example here illustrating a table which has a primary key defined of sensor and date and timestamp. The primary key is divided into a partition key component and a clustering key component. So the partition key in this case is sensor and date, and the clustering key is the timestamp. So what that means is every unique combination of sensor and date forms a partition, and Cassandra will actually calculate a hash of those, which is used to look up which partition and find the partition and which node it's on. And then within the partition, there is a row per timestamp. And this is a pretty common structure I've shown here, where we have what we call a bucket by date. So the date is calculated out of the timestamp, is a pretty common strategy in Cassandra data modeling to limit the size of partitions rather than have them grow forever for, say, a sensor that's running for years on end. So in this example here, sensor 1 on the 1st of January, that partition has gone on to node 1. And then you can see sensor 1 on the 2nd of January has gone on to node 2, and sensor 2 on the 2nd of January has gone on to node 2. So the entire partition has to be stored on a single node is a key concept to understand there. What that means is if that your partitions get too big, and we'll talk in a second about what too big is, it can cause issues where nodes are too full or aren't balanced properly, and other issues as well. Also, the partitions is the way that Cassandra scales out. So as we add nodes to a cluster, the partitions are divided over a larger number of nodes, although each partition is still on a single node. So if you have a very small number of partitions, that makes it very hard to add nodes and scale out. There won't be enough granularity in the partitions there. Oops, just on to the next slide. So, as I said, if your partitions are too large, it can cause issues, and this is kind of the first issue I was going to dive into here. So when you have over large partitions, you'll often see that showing up through long garbage collection pauses. So garbage collection being a process that the Java virtual machine does to reclaim memory, and garbage collection pauses can cause the Java virtual machine to stop doing actual work while it does GC for a period. And also difficulty streaming data to new nodes. So if you see your cluster stopping for a minute, or if you're trying to add new nodes and the data streaming is taking a long time, both of those things can be symptoms of over large partitions. Typically, the other way that you can find out about large partitions is a data model review. So one of the things that we often do is review people's data models, and you can see where partitions have not been designed to keep them small enough. Also, there's tools, node tool CF stats and node tool or table stats, as it's known in the more recent versions, and CF histograms, which provide information on partition size. And the recommendation that we have is less than 10 megabytes per partition is pretty safe. Less than 100 megabytes, you're probably okay. Above that is likely to start running into problems. There has been quite a bit of work in recent versions of Cassandra to improve large partition handling, so you possibly can get away with a bit larger, and we certainly have seen a lot larger, but they're good measures for safety. There are also log file warnings about compacting large partitions, which will tell you when your partitions are too large. So all of those things are signs to look out for, and signs that potentially you have an issue with your data model and the partitions being too large, so not bucketing enough, or other issues with the way you've done the data models. So how to correct that? I mean, generally, it's probably going to require a data model change, which is not necessarily a simple thing. So it's obviously better to catch this issue early during the design phase through data model review, so you have to change the data model and change the application to correct it. We recently published a set of tools called IC Tools, which can also help by giving you the actual partition keys of any large partitions and the top 10 partitions and those kind of things, which we've found pretty helpful in digging down and understanding where an initial data model review doesn't make it clear where the large partitions are coming from. And there'll be a link to those tools in the mail out that we send after this presentation. So the next common issue and best practice for consideration I wanted to talk about was tombstones. So tombstones occur when a row is deleted in Cassandra, and it's basically a virtual delete. So rather than actually removing the data from a table, Cassandra writes a new record into the SS table saying this row was deleted. And that's because, I won't go into the reasons here. Tombstones remain in the SS tables and the Cassandra tables for at least 10 days by default. So there's a property called GC grace period, which is a property of each table in Cassandra, which is 10 days by default. That guarantees that the virtual delete will stay on physical disk for that period for at least 10 days. It can stay longer because compactions, which we'll talk about in a few other slides, compaction has to occur on the table in order for the tombstone be removed, and how long that takes depends on your compaction strategy. But the idea of tombstones is to make sure that, according to replication and consistency levels that we talked about earlier, when a delete occurs, that delete has had a chance to be propagated to all of the replicas in the cluster before the record of the delete, the tombstone, is removed from the cluster. So a higher ratio of tombstones to live data can have significant negative performance impacts. It means that when you do a read, that there's more data that has to be scanned through before the final results can come up, typically spread across SS tables, and generally a high ratio of tombstones you'll see creates pretty poor read performance. So tombstones can be created. Deleting data is the obvious one that creates tombstones, but you also need to be aware that if you update a column or a cell with a null value, that will create a tombstone. And also updating of collection data types, depending on the approach you take, can create tombstones as well. And that last one is a bit of a trap that can be unexpected. So there are tools to help you diagnose where you've got high levels of tombstones. The CF histograms give you a ratio of tombstones to live cells as one of the stats that they provide. There are also log file warnings when the ratio of tombstones to live cells is too high. The general symptom, which I probably should have mentioned, is slower than desired read performance, and then you can look into node tool stats to see if tombstones are an issue. The other place where tombstones immediately spring to mind for me is if you have suddenly slow read queries, particularly after you've done a bulk delete. But it's in the clusters that we manage. If somebody suddenly says, "Oh, my reads have suddenly got slower in the last hour," a question we often ask is, "Have you done a big delete?" And that's often the cause. So if you're managing a cluster and you suddenly unexplainedly see queries get slow, potentially somebody's done a bulk delete and created a lot of tombstones, which can cause that issue. So how to correct the issue of too many tombstones? One thing that can help is tuning the compaction strategy. So level compaction strategy and time windowed compaction strategy, we'll talk about those later, can help in the right circumstances. So basically by doing more compactions, the tombstones get removed more quickly after the GC grace period, after the 10 days has passed. That can help in sort of marginal circumstances, but it's probably not the end solution. In an emergency, so if someone's done a bulk delete and basically destroyed the read performance of your cluster, the best approach is probably to reduce the GC grace period, and you can reduce that to a very short period of even a few seconds, and then force compactions to get rid of the tombstones out of the SS tables. There is a risk when you do that. The tombstones do hang around for 10 days for a reason, which is to stop what they call resurrected data, so loss of the delete operations. So you are taking that risk, but in the case where your cluster has become unresponsive because of too many tombstones, it's probably an approach that you'd still consider taking. Long term, really, the approach is to review your data model and your application design to reduce the amount of tombstones that you're reading. Hopefully, firstly, by reducing the number that you're creating, but also potentially by targeting your queries better to not be scanning over tombstones is another approach that you can take to reduce the impact of tombstones. So the next thing I wanted to talk about was compaction, which I briefly touched on the last slide. In Cassandra, SS tables, once they're written to disk, are never updated. So SS tables are the tables that store the actual data in Cassandra, and a key sort of principle about how Cassandra works is that those tables are just written once and they're never updated. What there is, though, is this process called compaction, which picks up, if you like, older SS tables, combines them together to create one new consolidated SS table. So the way I like to think about Cassandra SS tables, and this is kind of a logical view rather than physically exactly what they are, is that they're really transaction logs that are reconstituted when they're read rather than actual values of the data. So the example shown on the right of the slide there is that we have one SS table which says that a row with key value 1, 2, 3. At 1 o'clock, it was set with the value of column 1 was set to A and the value of column 2 was set to Z. And those two things were written, at 1 o'clock and written out to SS table 1 when the flush occurred. And then sometime later, at 10 past 1, we came along and updated for key 1, 2, 3 the value of column 1 to B. So before a compaction occurs, if I want to know the value of column 1 in row 1, 2, 3, Cassandra is going to have to go away and look in SS table 1 and SS table 2, basically combine the effect of those two writes together and come up with the answer for me that for row 1, 2, 3, column 1 equals B and column 2 equals Z. So over time, what can happen, or what would happen if we didn't have compaction and we had doing lots of updates, is that the values of any given row get spread over a large number of SS tables, thus making our reads really slow, because every read is a seek on disk, which is a relatively slow operation. So the compaction process is basically consolidating those SS tables, doing what we would have to do at read time, but doing that in the background into a physical record in a new SS table, to shortcut that process when we come to do a read at a later date. So in the example here, when compactions run, it takes SS table 1 and SS table 2, creates a new SS table 3, and forgets about the fact that column 1 was ever equal to A at 1 o'clock, because it was overwritten to B at 1:10, and just puts that result into the new SS table. And we have a single record in one SS table now, which when we do a read, we can look that up and get the end result there. So the compaction process, to be clear, takes those two SS tables, SS table 1, SS table 2, creates a new SS table, it's called SS table 3, and then just throws away the two SS tables. So although SS tables are never changed on disk, they do get thrown away with the data being written into that new consolidated SS table. So the other kind of things to know about compaction, it is an ongoing background process in Cassandra. So sometimes you have people ask, can we schedule when compactions run, those kind of things? No, it's an ongoing process, and the compaction strategy determines when that occurs. And it's not in any way compression. I think common when you first hear compaction to think maybe it's compression. It's not really compression, it's logical consolidation of data there. So compaction strategies, as I mentioned about, determines which files Cassandra picks up to compact and when those compactions occur. So choosing the right compaction strategy, and to a degree tuning the configuration of those compaction strategies, can make quite a difference to the performance of your Cassandra cluster, and particularly the read performance of your Cassandra cluster. So there are three compaction strategies that are supported: size-tiered compaction strategy, leveled compaction strategy, and time-windowed compaction strategy. And time-windowed compaction strategy is basically a replacement for date-tiered compaction strategy, which still exists but is deprecated now. Time-windowed compaction strategy is sort of a simplified version. So basically, how do you know if you've got your compaction strategy correct? So the main issue that you will see if your compaction strategy is wrong is that you're getting slower than desired reads, or that old data is being retained on disk. Particularly if you're using TTL data, you'll see you'd like your data to be disappearing from disk more quickly. It's not going there. You can see, I guess the flip side is that you're spending too much effort compacting, although the slower reads is by far the more common issue that people report and see. So the other tool available to diagnose that is the node tool CFstats, which has an SS tables per read statistic. So that tells you on average, and also the histogram shows you percentiles, how many tables is Cassandra having to go and open in order to, or how many files is Cassandra going to have to open in order to satisfy each read. And ideally, you really want to be that to be 1 or 2 SS tables per read to have good read performance. If it's much higher than that, then that's likely considerably slowing down your reads. So one slightly glib rule of thumb is that if you're using side-tiered compaction strategy and you're having issues, you're not happy with how fast your reads are going or other things like that, then look at leveled compaction strategy. So level compaction strategy is, the main difference is that level compaction strategy, when it chooses what tables to compact, tries to keep partitions together. SS size-tiered compaction strategy is less concerned about trying to bring partitions together, and that kind of just happens by luck in size-tiered compaction strategy. So the main thing to be aware of with that is that the compaction overhead with level compaction strategy is higher, considerably higher than it is with side-tiered compaction strategy. So Cassandra will spend more effort, more CPU cycles, more I/O throughput on doing compactions with level compaction strategy than it will with side-tiered compaction strategy. So if you're going to make that change, you need to be sure that you have the capacity available in your cluster in order to do that extra processing. You can also look at the time-windowed compaction strategy if that fits your particular usage of data, and typically that's time series data with a TTL on it will fit time-windowed compaction strategy, and works very well when it's well aligned with the data and well tuned. To change your compaction strategy, it can be changed online, but can result in significant load due to recompaction if you're not careful about how you do it. So if you just jump in and do an alter schema and change a compaction strategy, that, unless you're very sure and confident of what you're doing, can result in a wave of recompaction occurring across the cluster and causing significant load. So definitely need to be careful if you're thinking about changing compaction strategy. One good method to update the strategy is you can use JMX to update the compaction strategy for one node at a time before changing the schema. And there's blog posts around on the internet about how to do that. So that means that you can just have a single node, redoing its compactions, work your way through the cluster. Once they're all done, change it at the schema level so it becomes a permanent setting. And that way you don't have that big load across the entire cluster at one time. There is also a thing in Cassandra called write survey mode, which you can use to test changes in the write overhead as a result of changing compaction strategy. So write survey mode allows you to add a node in the cluster which receives writes but doesn't get involved in reads or quorum calculations at all. So basically won't affect the cluster if it has problems. And so you can put that into your cluster, change the compaction strategy using JMX, and see, measure what the actual additional overhead is from changing your compaction strategy. Okay, another important topic in terms of best practices is security, getting away sort of from tuning more into setup here. We would say that the minimum you really should be doing for most Cassandra clusters is, well, first of all, enabling password authentication. That's a pretty simple one, and it gives you at least some control over people accessing your cluster. In most cases, enabling client to server encryption, TLS, is also a good minimum practice. You possibly can get away without that if you're confident that you have a very secure internal network that you're using. But again, not necessarily a huge overhead to enable, and a worthwhile extra security step so that your password's not being sent in clear text. Similarly, enabling internode encryption. Again, if you're on a very trusted network, perhaps not necessary, but in most cases worth doing. And don't use the default Cassandra user. So the same with any database would make the same recommendation. Using the default user makes it that much easier to guess your password and so forth. But also the default Cassandra user has different rules about how many nodes, the consistency level of the query in order to authenticate that user, which makes it more prone to not working in outage situations, which is exactly when you want to be able to log in. So we definitely recommend, first thing you do is when you create a new cluster, is to create a new user and use that as your login. And of course, ideally, having super users for admin purposes and less privileged users for application usage. The further best practice that we recommend is to encrypt sensitive data at your client or application level as much as possible. This one actually, to some people, again, if you come from a relational database background, seems a bit not obvious because you want to be able to do joins and those kind of things and on parts of the keys, which, if you encrypt the data, become very hard. But with Cassandra, once you think about the typical access patterns where we're using a primary key value, which is getting hashed anyway, and we're just doing equality lookups on those values, there's really very little loss of functionality by encrypting that data before you put it in Cassandra. And there's obviously a considerable gain in security the earlier in the stack that you were closer to the client that you actually encrypt that data. So you can encrypt the data, and then it's becoming hashed anyway, so you use that to look up the primary key values and other equality checks. And obviously, if it's not a primary key value, then it can be encrypted as well. The only real case that you then have to think about is where you're doing range selects, so greater than and equal than, typically is dates. And once you look in most domains, if you've encrypted all the identifying information, social security numbers, addresses, names, those kind of things, then dates are not particularly sensitive data, so you can leave those unencrypted to still do range queries on those where you need to. So definitely that's a practice that we encourage people to think about in their application design, is doing that encryption in your microservices layer or your application layer. There's also a company that we partner with called Baffle.io that have an encrypting driver for Cassandra, which does that sort of transparently for you as part of the connecting to the cluster. So now looking into testing as well. So we've done design, got our security there. How do we go about and test the application? And there are a few things that, again, if you come from a relational background or other application background, that special considerations that you want to think about when you're testing, and particularly load testing Cassandra applications. So firstly, make sure that you're thinking about background load. So one thing that's very easy to do with Cassandra, you can push an extremely high write load for a period of time, but then sit there and watch the cluster take forever to catch up with compaction. So when we do benchmarking quite often here, and it's pretty typical to spend 4 or 5 hours pushing to create a base load of data, 4 or 5 hours pushing writes as fast as you can to get that data in there, and then have to wait a full 24 hours for compactions to catch up with that data. So don't be fooled if you're running a load test into thinking that your write throughput over 2 hours is going to be replicable, going to be sustainable over weeks and months. Also, when you're running your load tests, don't forget about repairs. Repairs are a regular process that needs to be run on a Cassandra cluster to ensure consistency between the replicas, and they do take processing capacity and sometimes significant processing capacity to complete. So when you're running your load test, it's a good idea to actually run repairs during the period that you're running the load, particularly if you have a very consistent load and you don't have down times to run repairs or low load times to run repairs. Secondly, make sure your data volumes on disk are representative to what you expect in production. So one common mistake which we made in the early days, and which I've seen other people made, is you run read and write operations at the level you want, but you have only a small amount of data on disk. You can get really good throughput results, but actually what's happened is the small amount of data that's there has been read up into the operating system disk cache. Everything's operating in memory and works really well. And then once you get to a size where you're not fully cached, performance drops off dramatically. So make sure that the data volumes you have on disk are representative of what you expect to have in production. That way, it'll reasonably well marry the cache hit rates that you expect to see in production, which can make a big difference to performance. Mirror the production data demographics as closely as possible. So we've talked about partition sizes and all those kind of things making a difference to performance. Obviously, you want those there in your performance tests. Update and delete workloads. Again, we talked about tombstones and the impacts of those. You need to try and replicate those in your performance tests as much as you can. And finally, in most cases where you're just using core Cassandra features, you can probably be pretty comfortable relying on linear scale up. So you could perhaps test on a half-size cluster and be comfortable that you're going to get double the performance on a cluster twice of that size in production. But there are some features that you want to be wary of if you're relying on that scale up. Secondary indexes is definitely one. It's very easy to construct and use secondary indexes in a way that kind of defeats Cassandra's scalability. Materialized views, in theory, don't have that issue, but being relatively new, I'd still be pretty wary if I was using materialized views and relying on scaling up. I'd want to test those pretty close to my production scale. So, final slide from me before we get into questions. The obligatory Instaclustr plug, which I saved for the end. How Instaclustr can help. So Instaclustr, our core of our business is providing Cassandra as a managed service in the cloud. And we also provide Spark alongside that as part of our managed service as well. And basically you can come to our website and give you a best practice, as we talked about before, configured Cassandra cluster in less than half an hour. So select a few things, click go, probably 10 minutes, even less. The cluster will be configured, and then we take care of all the ongoing management for you. We support AWS, Azure, GCP, and SoftLayer as cloud providers. The security configuration that we talked about before is basically a tick of a box when you set up your cluster and all of the certificates and stuff are set up for you. We have monitoring built into our console to give you access to a lot of those statistics that I talked about from a best practice point of view, and a cluster health page which automates checking against a number of those key indicators that I talked about as best practice health there, things like tombstones per read and those kind of things. Of course, we also have a very good ops team that provides 24/7 response to alerts that we get to get in and fix any problems that are there, and also to answer queries and help you out along the way with Cassandra. So that's the managed service. Based on the managed service and what we've learned through that and our expertise there, we have nearly 1,000 servers that we run under the managed service. We also provide consulting, where we can do cluster health reviews against the kind of best practices that I've talked about, and data model review, help with performance testing, those types of consulting services that you expect. And finally, we also provide enterprise support. So where you're in an environment where you're not running in the cloud for security reasons, or perhaps you have very sensitive data, and you don't think the managed service is the right choice for you, we can provide enterprise support contracts where you get access to our tech ops and support team to help you out with any issues you have managing your own cluster. So with that, and right on 45 minutes, I will turn over to Gina to ask the questions.
Thanks so much, Ben. That was a great presentation with a lot of great content. We have gotten a lot of questions in, so I will start at the beginning. Given that LCS is much more CPU intensive than the other strategies, is there a good use case workload type that it's good for?
So there is a bit of a rule of thumb that I've seen around of use LCS when your ratio of reads to writes is at least 4 to 1. I mean that's one way of looking at it. The other kind of way I look at it is how much do you care about read performance. So yes, it's a price to pay, but if you care about fast reads, then it's just a price that you have to pay. Is kind of my opinion on that, and it comes down to your application and business requirements about how much are you prepared to pay in terms of processing capacity in order to get the read performance that you use.
Great. The next question is, what are the key metrics that you use for monitoring?
Yeah, so I guess the number one, well, there's a number of metrics, but latency, well, actually, let's step back one step from there. One of the things that we've done in the last sort of 12 months with Instaclustr is introduce what we call synthetic transaction monitoring, or generally known as that. That actually, what we do there is write into a small table that we control, do a number of reads and writes every 20 seconds, which gives us a very controlled way of monitoring the performance of the cluster independent of the performance of the data model and what the application is doing to a fair degree. So with that, we can monitor the latency of those queries, so the read and write latency, and just the pure success of those. And we also monitor that for the application tables as well, but it's a little harder to tell there whether that's expected changes or whether it's an issue. Other key things that we monitor are the number of pending compactions. So if a cluster is getting overloaded, the Cassandra will have a queue of compactions to complete, and that can result in a kind of cascading failure as the number of pending compactions gets worse, the amount of work required to do each read increases, and they cascade into each other and eventually can result in big problems in the cluster crashing. So that's definitely a key one to look out for. And then disk usage, an important one. You definitely don't want to fill up your disks, and just state of the processes and so forth. There are more that you can monitor, but I think if you've got those ones covered, you've probably got some pretty good key health indicators, and then you're drilling down into other metrics to really understand more what's going on.
Great. Another question that came in is, can you expand in more detail on when time-windowed compaction strategy is appropriate and what to look out for?
Yeah, so I mentioned quickly there, time-windowed compaction strategy and its predecessor date tier compaction strategy are basically designed to support time series type data, and that example that I gave earlier with the sensor and the time and a value is an example of time series data. They're very good when you're then going to query, well, when your partition key and you corresponds to a time range, and your partition corresponds to a time range. So you don't want partitions that live for a really long time, because with time window compaction strategy, your SS tables align to writes from a time period. So if your partitions get updated over a really long time, they'll get split along a lot of SS tables. And you also don't want to be doing queries over a really long period of time. So where you're writing time series data and then you're just looking up on relatively short periods of time, and your partitions live for short periods of time, and ideally you're doing TTLs, so you're not keeping the data forever, those time window compaction strategy can work very, very well. We used it for a number of clusters with great success.
Another question that just came in, and keep writing in your questions as you see fit. What happens if two servers are in different DC and both are seed nodes and one node goes down?
Yes, there's a common misconception that seed nodes have some special role after the cluster has started. So the only purpose of seed nodes is to be the initial other server that nodes contact when they first start up. So it contacts a seed node, then the seed node, and then it joins in what's called the gossip protocol. And from that point on, all of the nodes in cluster are talking to each other, and the seed node plays no real role at all. So a seed node going down is no different for another node going down once the cluster is up and running. So just trying to find that question. Two nodes are in different DC and both are seed nodes and one node goes down. Yeah, so one node going down, whether it's a seed node or not, if you're using a replication factor of at least 2 and depending on your consistency level, there's no real issue as a result of that node going down. It's just a standard thing that happens, and Cassandra will keep on running if it's configured well.
Great. Another question that has come in is, do you have any tips specifically for running Cassandra in AWS?
Yeah, so we obviously use AWS a lot, and the majority of our servers that we run are in AWS. I guess one of the things that we've found over the last, it's actually more than 12 months ago now that we moved to using EBS in AWS rather than instance-based storage. It took us quite a lot of tuning to get that configuration correct, and based off a lot of work that others have done as well. But we have found that the manageability of EBS-based nodes is a lot better in AWS because you do less having to stream to repopulate nodes and those types of things. Here's some other tips. Other things that we do, for example, is aligning our Cassandra rack definitions with AWS availability zones and spreading the cluster over multiple availability zones so that we can keep availability in the face of a loss of a complete availability zone.
Great, and I think we have time for one more question. Are you collecting rolling up Cassandra trace data at regular intervals so users can consume that data to debug performance blimps?
No, we're not at the moment creating, so if by trace data you mean query trace data, we don't collect that data. We do collect and roll up into a Cassandra cluster using Spark a whole pile of monitoring metrics which can use to go back and investigate things, but we don't have any centralized query tracing collection. There is some stuff on our roadmap to do more in that space, but not there yet.
Okay, and one more question and then we will have to stop, but keep writing in your questions and we will get back to you after this webcast with any questions that we don't answer. So the last question is, when setting up nodes on AWS VMs, is the concept of racks still valid?
Yes, as I think I mentioned there, we map Cassandra rack to AWS availability zone. That way your replicas your data replication spreads across multiple availability zones, and you can build a cluster so that if a whole availability zone goes down, as does happen from time to time, your cluster will still operate fine during that availability zone outage. And we've been through a few of them now and proved that concept works quite well.
Great. Well, thank you so much, Ben, for your time. I really appreciate it, and I know that there was a lot of knowledge that was passed on. For those of you, again, that didn't get your questions answered, we will reach out to you shortly with answers to those questions. Thank you so much for joining us. Be sure to, before you leave, look at the attachment section for more content and for the slides of this presentation. Thanks again, and we look forward to hosting our next webcast soon. Thanks so much.